I was happy with that. All right, so get this back. Is this me? Yes. Oops. And then I wanted to also go just to just go to this. So yeah, this is the first part is just like kind of do this, just do this same thing, you know, just kind of go through that, go through actually both of these ideal and the regular. It's just like some bookkeeping thing. It isn't, yeah, for the part A thing. It's like using the statistical thermodynamics. So it starts with the partition function, and then it kind of gets an ideal solution from partition function. And the other part is the same, you know, the other part is the same thing. I mean, the other part is just end up with the Hildebrandt parameter. I mean, it's the same thing. I guess the difference is there's no difference. The regular solution part, I think, is just the same as what we did before. Right? And that part we had already. Then, you know, there's a kinetics and thermodynamics. I kind of talked a little bit about kinetics. You can, there's three things you can do with kinetic: is this grain boundary mobility, solute drag, Zener pinning, and porosity drag. That's what he means by, he says like you can have kinetic stabilization, right? So that's what he means by that. So that, all right, so the weird thing is that, like, if you think about those kinds of pinnings, like the thing he ends up with, it looks kind of like the same thing almost, except it's a thermodynamic model. It's almost like you look at two things, either from a kinetic perspective or from a thermodynamic perspective. I think that's part of the thing going on here. Is that he skims over the kinetic, but basically the model he ends up with is basically could be a kinetic model if you wanted to look at it that way. So anyway, so he's gonna so this other paper, Weissmuller from what's in the 60s, the 93, I guess. See, he's talking about the same thing. Like you can have, so there's three ways to kind of have grain boundaries. You can have pure like alpha, pure beta phase, so like copper and zinc crystals, or you can have a substitutional solution, and you can have gradients in this, the kind of degree of substitution, or you could have this kind of thing that looks just like a Pickering emulsion. In other words, this is how you'd make a colloid if you put powdered sugar in to stabilize your goo that you put in, you know, fat or something, right? So anyway, and this would be like that would be the Zener pinning type kinetic model. In other words, wouldn't be a stable system in that case, right? It'd just be that these particles, which can be macroscopic and micron size, even hundreds of micron sized particles, can stabilize the interfacial region mechanically, kind of, more or less. I mean, there's interfacial tension issues. Right. So those three things. So that's question something here. Like, look at that Weissmuller, which he cites, I think. So this is kind of like the basis of this paper. Figure one shows three scenarios. So how does Saber account for those three possibilities? Okay, so kind of like he's got these three cases. So this case, this is like UA, UB, like that's the free energy of one phase and another phase. So he's going to talk about, so there's no mixing here. In other words, this is before mixing. I would say it would be like in a normal situation, you'd have like water, oil on the top and water on the bottom, and it's not mixed. Right. So that's a free energy oil, free energy of water. When you shake it up and somehow you have some way to make it miscibilize, then you have some possibilities of, so the delta of mixing is going to be this thing minus whatever the total is, right? So you have to calculate this and subtract off the free energy of each of these things. And you have the delta G of mixing. That thing you can minimize. You try to find where that thing reaches a minimum. So you can get the let's see, is Weissmuller the one that has those plots on it? Yeah, so he's going to get like a minimum, in this case, versus particle size. So free energy versus particle size, he has a minimum. That's the magic size where you have a metastable nano, so it's 150 angstrom grains. So that's probably small enough for the Hall Petch thing to give you super plasticity, some kind of super mechanical properties. Right, so anyway, so this is an earlier version of the whole thing. So there's like 3 versions where they ignore various aspects of this, and then this version of the saber includes all of them. So he's got, because he's looking at delta G, delta U, so he's got the U of the pure components and the U of the U of the blended components and the U of this. So he's got 3 things. So the delta U means he's already included the base thing. He's already included this state. That's what he's comparing with. So it's comparing this with that or this with that, right? So he's got the free energy within these domains. And he's got the free energy of this interfacial region that he defines as a separate region. It's got a volume to it, right? And also, so normally you have like all the energies between the A and B components. So these are all things that everyone, like, so you're going to get like a huge number of different thermodynamic models, and then all of them are going to deal with the same issues, like what is the coordination number, that usually called small z, right? But so like how many neighbors does this guy have? Well, you see like this missing neighbors in this interfacial region. It's like a defective area, right? So basically there's going to be, and also there's going to be a difference in the energy of interactions here, right? So he accounts for that with this alpha term. So he multiplies all those. So let's see, make this larger here. So he's got this kind of interfacial, let's see, what's that letter, T or something? Oh, IG is the interfacial part. B, I think, is bulk. B is bulk. T is transitional, and intergranular is here. So he's got like the region where the transitional between the bulk and this intergranular. He's got 3 free energies here, right? And each one has a certain, say you count how many atoms of A, how many atoms of B, and then how many AB bonds and BB bonds and AB bonds in each of them, right? So how many of those and the energy of those. And the energy of an AA, if it's in the interfacial or in the transitional, is going to be alpha times the energy in the bulk. So this alpha allows you to have kind of different bonding. Alpha is a garbage can. It can be anything. It's whatever the difference is between the interfacial and the bulk. Alpha is going to be less than 1 usually, this system, right? So he's got this alpha term to be able to fiddle with this, and he has the thickness of the interface term. So he's going to, in the end, come up with a big free energy expression. He's going to take derivatives with the fraction that's in the bulk, the fraction that's in the intergranular, and then this F number, which he gets from equation 12. So equation 12, F is the volume fraction of the grain boundary region, which comes from this equation, which he says comes from reference 22. Reference 22 is this Pablo Thorpe Oss from some 1990. That's right. It's like here somewhere. Pablo Thorpe Oss. Right? And they say, here's this equation. Like they don't say where it came from. If they do mention this reference 20, like there's no calculation here. It's just like find the relation is obtained for the total intercrystalline volume. Boom. And they say it comes somehow, it's related to the tetrachedecahedron, which I should be able to figure that out, but this one, tetra's 4. Tetrachai is the word that's good. Deca's 10. Yeah. So it's a 14-faced polyhedron. Okay, that's handy. So you can find that he references 20. That's this paper somewhere. That's the same paper, right? That's from this book, right? So it's like page 211 on this book. And you find out like that's not going to do you any good either. But I'll demonstrate that, I guess. Like you get to that book. Oh, now this guy's jammed up. Oh, there, it's happy. So anyway, the only part that mentions Tekka di whatever, 14 faced, is this thing, and that's not helping any. That's just like an equation for the volume, right? I mean, it's just a constant times a cubed. It isn't even anything different than d cubed is the volume of whatever, right? So in fact, they're all just some number times a cubed. So like this isn't giving you anything really. It'll give you a constant factor, I guess, because the a cubed would have a prefactor for a sphere. So basically the difference between this number and the sphere number might give you some number, but that's just a constant number. Like the a cubed part drops out. So anyway, it's a rabbit hole. It doesn't go anywhere as far as I can see, but you guys figured it out, though, right? I mean, if you figure that equation out yourself, you don't get, at least I don't get the same equation. And that's kind of a problem because his whole thing is based on doing these three derivatives. So he's got the amount in the bulk, he's got the amount in the interface, and then he's got this F number, the fraction, kind of the balance between the interface and the bulk that he calculates with that equation 12. And then he also says there's a mass balance. So you have to have, it has to either be bulk. The original amount you put in has to be the bulk in the interfacial governed by this fraction that's in the interface. Right, so he's got four equations, and then he can find the minima in that thing. These are given a minima, just like this other one gets a minima, but he only gets a minima with just one parameter. Right? He just gets it in terms of the size of the, he just gets it in terms of D. So he finds a minimum in terms of D of a simpler free energy expression. He's finding the minima in terms of all these things. And these things link together through this other equation. So he's got more parameters, but he's got more equations. And then he can kind of solve it that way. So that's kind of that's basically, it's kind of an interesting example of how you can apply these kind of simple Hildebrandt model and then just kind of add on features to it to try to get an answer to how big is it, how do you get a nano-sized grain? So then his parameters to manipulate are these energies of bonding energies between the components. So if you wanted a nano-sized grain, then I guess he'd play around with those bonding energies somehow, which you're kind of limited to in the system you're working with. So basically all you can do in the end is just calculate what your grain size should be if it will reach this metastable equilibrium, because you can't really change the materials. Like you can't change those energies ad hoc, right? So anyway, so it's, I don't know, NSF funded it. So I always look at the bottom, like where did they get money? So it's like basically NSF funded it. And so the first two numbers of the year, 2010, and then in 2013, it's a three-year grant, and then they spit out this paper. So that's kind of how it works. So anyway, it's this interesting little thing that has something to do with the chapter. So the logic behind the thermodynamic model is that you can balance out these energies and find a local minima if under the assumption that you have a grain boundary. Right. So you're introducing this, it's like the Gibbs equation when you introduce a surface, and then you can minimize to find the surface area for certain surface energy and bulk energy. So same thing. It's kind of the same thing here, but you introduce this intergranular region and then minimize it. Right. So that's the logic behind it. It's a Gibbs approach. It's basically Gibbs free energy approach to solving like how the grain size would get. And then Weissmuller shows the three possible scenarios. So how does Saber account for those three? So he does it. So the ground state one is accounted for because he's talking about change in free energy. The base one is that state one of this thing. In other words, the delta G is between the first picture and the other two. And then he's got a free energy expression for this thing, and he's got a free energy expression for this interfacial thing. So he's not, those two things are the two things he's taken the minimum of, including also like how big is that interface. So here the interface is one atom, but for Saber the interface can change size, and that's this Fig number. That's the size of the interface. So you can have the free energy of the interface, free energy of the bulk, and the size of the interface. This last cartoon actually has two terms, and then he has a mass balance to say like it all has to add up to what I put in at the beginning, which is the first picture, which is your base free energy. All right, so that's kind of what's going on there. Then let's see. So he's got an elasticity term in here. So, and then he's got these energy AB terms. So the energy AB, the chemical advantage is the mixing energy, this EAB, EBB, EBEAA. That's like the chemical interaction thing. Then he's got this energy elastic here. This is that's a Saber, right? Yeah. So somehow that energy elastic is in his free energy expression here. When he finally gets to the equation, he's got the elastic, and all this business of EAA, EBB is the chemical energy of the thing.
You mentioned at section B,
oh yeah, the elastic is here, mixing and then elastic. Right, good, thanks. So anyway, he does the same thing, and he mentions in the beginning he's like not the first one to do this. So like there's a long group of people that have kind of looked at grain sizes, trying to get grains smaller and figure out this thermodynamic model for grain size. So then derive Saber's equation 12. I think, or you guys derived it, right, with spheres, right? So if you look, all right, I mean, you said you did it, so I believe you. I think it looks like a pretty simple expression. It definitely does not look like you need to have any kind of weird
It made sense when I looked at it.
14-sided thing to get this equation, right? Because there's no 11.37 on this, the volume times a cubed to get the volume, right? So, okay, so, but he says in three-dimensional polycrystal, grain boundary thickness T, grain shape factor proportional to D. Okay, so grain shape factor can either be the aspect ratio, it's like to take the largest, in other words, they're asymmetric. If there's a shape factor, they're asymmetric grains. But the way you did it, they're spherical grains, right? And you got this equation. So this grain shape factor is a red herring. It's like leading you down the wrong rabbit hole, I think. Anyway, the more I looked for some time at this grain shape factor, that didn't help me. And then he says something about, oh, he refers to reference 22, which talks about this 14-sided grains. Then they're talking about if you take the 14-sided and then you inscribe within it a sphere, then the difference in volume between the 14-sided and the sphere is the Ig. That's the interfacial grain. So they aren't going to be the same volume. There's a little bit of a difference because it's like a soccer ball with the faces, right? So anyway, that doesn't take you anywhere either. So, or you can, when I did the sphere calculation, I didn't get this equation. I got an equation that looks almost the same, but it's like, I think it's T minus D or something here, and it's plus instead. I don't know. It comes out to a different equation. Let's see it. May I have it here? So anyway, and this same equation though is given by this guy, like it's given right here. He also doesn't derive it. So maybe you can derive it. I couldn't do it yesterday. If you can derive it, that's good. Or you can say, like this equation was a typo and he just copied it, put it here, and made it the basis of his whole theory, despite that he got the NSF grant and whatever, right? So that's the conclusion I came to. So like this thing can't be derived. But right, if you plot this out, so you can plot it out and it looks kind of like this. Let's see, this FIG versus diameter. So it goes kind of like that. So here. Looks like that thing. So then this would be FIG 1 and 0. So it's like what is it? -1 minus D minus T or something over D cubed. It's like that. So basically so it kind of works like when T is 0, then this is 1 and that's 0. So when you have no interface thickness, then you have 0 amount of interface, volumetric of interface. When T is D, then this is 0 and you have 100%. You have 100% interface. Like when the diameter of the grain is the same as the thickness of the interface, then it's just all interface. And if you plot like log of FIG versus log of B, you get a straight line. So this is basically a log dependence. So that means that FIG is basically proportional to the thickness to some power. So it basically ends up being a power law, the way that works. But anyway, so whatever that's worth. I thought that might have an answer to whatever this equation meant, but that didn't help any either. It behaves the right way, but wait, if you can drive it, it's good. If you can't, just go back to saying that this guy originally lied, and then this guy where it came from, and that if that's true,
Which paper was that other one? Sorry.
it's linked there. So it's called. This is Plambow, Thorpe, and Augst. It's linked there. It says like where the equation 12 came from, but that link was dead. I just fixed it. So it's actually there twice now. But and then this guy references this other book thing, which is just an equation for tetra, whatever, 14-sided, which doesn't give that equation. So none of it leads anywhere that I could see. Maybe you can find better, but you know.
Well, so he mentions, yeah, that it's a sphere in the paper. So I don't understand why they even mentioned the tetrahedron. They don't even use it. They don't use that math.
Well, why does he talk about a grain shape factor, which means it's not a sphere? If it's got a shape factor, it's asymmetric. That's like an aspect ratio. Or it could be like the perimeter squared divided by the area is another shape factor. They all have to do with things that are asymmetric.
Yeah.
So if he's using spheres, then you don't have a shape factor. Shape factor is 1 in that case. So the whole thing about this equation 12 is suspect as far as I'm concerned, and I couldn't get it yesterday. Maybe you can get it. It might be really simple. It looks simple, so it looks like it would be really simple to get. If you can get it, that'd be good. But see, when you did it, you didn't divide by d cubed, you divided by d cubed plus t cubed or something, right? So it doesn't look like this, but anyway, if you got it, you got it, you know? So that's good. So it might be a way to get it. So it'd be good if you get it, but otherwise you can go down the route of saying like, it's not possible. So that's E. So E might not be answerable. So the answer might be like, can't be derived. Or it's not the right equation. It does have the right behavior, like it does go to 1 and 0 at the limits, but then coordination number Z doesn't seem to be constant between the interface and the grains. So that's like from the picture of this thing. So you can see like that red one only has 3 bonds, that red one has 4 bonds. So like the Z, the coordination number, that guy's 3, that one's 4, and 2D, right? So anyway, what's with that? So basically he accounts for that in this kind of garbage can, this alpha garbage can term. So he puts in a garbage can term to account for that kind of effect, and also that the bonds, this whole region could be almost like amorphous kind of, or could be like some different kind of structure, like highly defective structure for sure in the intergranular region. I mean, if you think about it, all right, maybe his picture is pretty good for what it would look like, but you can identify the grains. It's almost like you could take out pieces of grains from the material. So you'd think that there isn't any. Anyway, there's some connection, I guess, that holds the thing together, but so he's accounted for that with this alpha. So that's kind of simple. There's more than 5 things here, so some of them are simple, some are not. Then Weissmuller shows this G versus D minimization, right? So he's going to take the free energy, find the minimum, and then get his magic size. That's a metastable crystal size under those conditions. And then Saber has those 3 minimizations plus the mass balance. And then so why does he need 3 and the other guy can get by with 1? So Weissmuller, he doesn't even have an interfacial region at all, you know. Like his picture doesn't include an interfacial region. It's just the grains. So he doesn't have an FIG because his FIG is 0. Right. And he's got these, I think he's looking at like this kind of mixture, and there's no, he doesn't have an FIG. So he's only minimizing with respect to the grain size in this kind of distribution of the components. So it's a much simpler model. Yeah, that's the idea. So that's why it's necessary, because he has a more complicated model. And just minimization restricted volume fraction. Is this an equilibrium state? So it's a, I mean, it's a metastable state. So that's what it is. So I guess it's a local equilibrium. Like, so you can think about what using thermodynamics to look at philosophical question last part here. So you could say, no, it's not an equilibrium state, because the equilibrium state would be the thing, the water and the oil separated, and that's it. Grains wouldn't exist in an equilibrium state, right? I guess you wouldn't have an interface. So the equilibrium would be you get rid of all the interface. So he's balanced out the interface with this kind of construction. Right? So basically it's a metastable equilibrium he's reaching. Just like particle growth, when you use a surface, like the Gibbs-Thompson equation for particles, reaching a metastable particle size during growth, right? And then that the equilibrium state would be like it reaches it full, fills up the room. The phases fill up the room. Then there's the results that he has. So the grain size increases with temperature, and the grain sizes decreases with increasing alpha, figure 5. So he's got some results. This is one of them, but so you could do all the figures if you wanted, but this is one of them that seems like kind of should be simple, I guess. So the temperature dependence has got to be like entropy versus enthalpy, right? So that as you increase the temperature, the entropy increases over the enthalpy, so you tend to get kind of, I guess, more mobility or something of the things. So basically, it's a mobility, or somehow they're randomizing more, and somehow they reach a larger grain size. This metastable equilibrium size gets larger because the entropy part becomes more dominant. He shows the equation with, some point he says entropy, enthalpy here. So delta S mixing. So like the elastic part isn't at play here, it's just this mixing part. And that the T delta S at high temperature governs, and that makes the thing grow larger. according, and they, so the T, the entropy part is all the temperature terms here. Right, so somehow, basically when that dominates, that drives the phases to grow. And then the alpha part, so alpha means the energy's lower. So if alpha is smaller, so that, let's see, the arrow direction is the direction of increasing alpha, I think. Figure 3. Let's see. No, we're looking at figure 5. Right? Figure 5. So the arrow direction is blue, red. So alpha is getting larger. So when alpha gets larger, you get closer to the equilibrium. So the interface gets alpha equals 1. The energy of the bonds at the interface is the same as the energy of the bonds in the bulk. This means the bulk and the interface become the same thing. So there's no selection criteria to change the grain size of this. When alpha gets smaller, the interface, the energy of the interface drops. Somehow that drives the grains to grow. Should be the other way around, I guess. It should be that as the anyway, I guess you have to figure out why that is. Alpha should be the bond energy at the interface. So alpha is always in front of the interfacial terms, wherever the energy terms are. So if alpha is small, that means the interface energy should be lower. And that should lead to smaller grains, I think. Let's see, no. The grain size for the Gibbs-Thompson is going to be sigma over delta H. So this is like sigma, the surface energy, right? So alpha EAA is basically a surface energy, and EAA is an enthalpy, bulk enthalpy. And that by the Gibbs-Thompson, it's surface over bulk gives you the size. So is that right? I think that's right. So basically, it follows kind of a Gibbs-Thompson result that the surface by bulk gives you the phase size. So that means the bigger the surface, the bigger the surface energy. So the larger the alpha, the larger the phase size. Let's see. So larger alpha, smaller phase size. Well, you have to figure that one out. I'm not sure why that ends up. I'm not sure he doesn't say exactly, does he? Nanogray says more stable at higher temperatures. Anyway, you'll have to kind of sort that one out. I can argue the opposite. So alpha is basically the ratio, basically how the surface energy relates to the bulk energy. So here the surface energy is the same as the bulk when alpha is 1. And it looks like that gives you the smallest grains. So and when the surface energy gets smaller, you get larger grains, which would seem that you would get the, by Gibbs-Thompson, it should go the other way, but it's hard to tell how that works. Anyway, I think a comparison of the Gibbs-Thompson equation with particle size would be kind of useful for this thing. Let's see. Let's see if we got that right. Yeah, because it's going to be what? Area sigma times area plus volume times delta H equals 0. So yeah, sigma by delta H should give you the size. Oh, no, wait, there's a size term here. I guess it's the other way around. It's delta H by sigma. So it's consistent with the Gibbs-Thompson. Where's our phase size here? R is sigma by delta H. So alpha would modify, like this alpha times G is sigma. So R should go with alpha. The delta G's would cancel. And then, as far as I can see, R should go with alpha. I mean, it's just the result of his thing, right? So R grain size should go with alpha. Alpha gets bigger, it gets smaller. So it should go the other way by Gibbs-Thompson. So that's kind of what we got going here. He's got the opposite effect. So that looks like by Gibbs-Thompson, that shouldn't be that way. The temperature thing is okay, it gets larger with higher temperature because the entropy dominates, but the alpha dependence doesn't seem to be right. Not by Gibbs-Thompson. So anyway, that's kind of that thing. That's the last question there. So some kind of open-ended, like this 12 thing. You guys said you derived it, so that'll be good. So maybe you can derive 12. If not, it's got to be that it's a mistake that carried through 2 papers. And then this thing, the alpha dependence, I don't get that. The temperature dependence is fine, but the alpha is kind of weird. So the 2 things could be related. That maybe 12 isn't right. Maybe that's why he gets this weird alpha dependence. Because 12 is directly calculating his fraction of the interfacial stuff. So anyway, so that's all that for that thing. It's basically not totally like to do with this chapter. I mean, it's this chapter loosely, because it's got to do with like messing around with the energy of mixing expressions. So what else here? So we got a little bit more to do. Let's see. Get a little bit more to do in this chapter, kind of just look at a few models, but not much. And then I want to do like Thursday, like start looking at like simulation things. And then the homework for that is going to be just like do some molecular, like lamps, molecular dynamics simulation. You can just do it, like it's possible to do it on your computer. So it's like just some simple thing. There's actually a web page that shows you, takes you through step by step. So the next homework will be that stuff. And then
So it'll be like a normal.
No, it'll be like a do it simulation.
Yeah, just one, like, we're still in groups though. So
Yeah,
one
it's still in
problem
groups. Yeah. It's like 5 simulations, but they're all related. It's kind of fun to do. I mean, one is just like move a particle around diffusion, and then it's like make the particles do something. And
you have the links to those simulations on your webpage?
yeah, I'll put them up. Yeah,
Okay.
yeah. It's not hard. I mean, I actually had these 2 high school students do it. Started to do some stuff, so they did that. So I think you guys can do it. You have to, all right, the hardest part is you have to download the LAMPS framework for the molecular dynamics on your computer, and that takes like a little bit.
Yeah.
And then other than that, I think it won't be that bad. There is like a step-by-step thing on how to do it. It's just not. I talked to the guy who posted it, and he said it was for like an undergrad class.
Yeah.
But I think it's kind of like, it's more than that, I think, but basically it gives you a pretty good idea what you can do with the molecular dynamics, but it's not going to give you anything about density functional and things like that. So, but maybe it gives you a feel for what you can do, Anyway, so that's where we're going. Let me just
So the modeling one will be homework 13, and then it's the final.
yeah, then the final is like individual.
Right.
Yeah. The final will probably be 2 problems, 2 papers.
Okay.
Individual, whatever. So it'll count as 2 quizzes.
So we won't do the experimental thermodynamics, I guess.
Yeah, I mean, it's kind of like, we've already covered a couple things, like we looked at the Brillion thing, Brillouin thing, and like, we talked a little bit about DSC.
Okay.
I don't know, I think you're gonna do that in that lab class, right? Like you do something like DSC.
In Dr. Steiner's class, their labs, yeah.
I mean, I don't know. Does he cover that or not? I mean, I could skip the computer simulation and do that.
DSC, I don't think we've done that. That's more like polymers, I don't
I don't know, metals, isn't metal DSC in the characterization center? Yeah. So you do microscopy?
Basically, we're doing SEM, going on to X-rays, like diffraction or EDS, stuff like that.
All right. That's okay. Yeah, you should probably do DSC at least. Maybe like gas absorption would be nice too, like surface area things. Can't do everything.
Yeah.
There's too many machines, but 2 isn't really enough, I think.
No, I'm just trying to get a sense of what the class will be till
Mhm.
the end of the semester.
Yeah.
So that's all.
Yeah, I think I'm just gonna do well, no, we might have time to do some experimental, right? Because we have, what do we have, like Thursday, Tuesday, and then we have 2 more, so we have 4 more classes, right? And
This Thursday,
yeah, I
next week,
can
and,
cover some stuff, yeah. I mean, basically, we'll have some time.
well, there's also Thanksgiving.
Yeah, so we have this Thursday, next Tuesday, then the week after that, we have 2 classes.
Yes.
So there's 4 classes. So, yeah, there's enough to do both of those, I think, maybe a truncated experimental thing. Yeah.
All right.
That's
Yeah.
all right. No, it's okay. It's one of those days. Yes, let's see if I got. That's all I had on that homework. So let's see. So anyway, so I wanted to mention this stuff. So you have, so basically almost everything, like this paper, for instance, that we're looking at, right, is mean field. It's like this thing. So there's no specific interactions, right? Even though it's crystals, the whole theory, the Hildebrandt theory, is all based on this kind of mean field thing. So you're ignoring that things like kind of organize when they mix, like especially charged things, right, will organize. And you're ignoring in fact, you're ignoring that it's a crystal, even though it's totally organized, right? So there's something kind of weird about that. So you can see like this model that everything is based on is pretty simple. And so there's 2 approaches to this. You can go to this end, which is the approach taken in colloids, right? And you can say like, I'm going to start talking about how things interact and how they organize, which means to get the correlation function. And you're going to start a Fourier transform of that is a scattering, right? So that's the scattering, meaning elastic scattering, not Brillouin scattering, right? So, or Raman, right? So it's elastic scattering. Energy in is energy out, and just change the angle. So you get the structure from the angle by Bragg's law, right? So the transform of that correlation function, how things put together. In other words, a rod throwing thing, like do the 2 ends of the rod land in the thing that you're looking at, would be like a 1 and then average over all the possible tossing of rods into the material and get the correlation function as a function of the rod length. So if you have a crystal, that'll have spikes in it where you have the repeat distance, right? So you get a peak in it, like if there's a preferred distance, it'll show up as a peak. Or you just ignore that happening and just say like the things mix, so like the Hildebrand approach, and then you're going to get no peak because you've ignored that peaks exist. And in the Hildebrand model is going to be applied to things like crystals, like substitutional solution, where you're thinking about the copper and the zinc is just like in random places, just like as if it was a gas atom floating around. So it doesn't have any structure to it, right? Or so you can imagine like those complications, like the zinc organizes. So there's a super lattice. There's like two lattices on top of each other, the zinc lattice and the copper FCC lattice or something. And you have dilute zinc and somehow it organizes into a structure, right? Or you could have two FCC lattices like NaCl, right? We have the chlorines and the sodiums and they're organized that way, right? So there's many complications. Or you could have clustering of the atoms. You could have, instead of having just atom A, there's some kind of affinity of A to B, so A has clusters of B's around it, right? And then you can make a pretty complicated mean field approach. We're still talking about there isn't any peak in the scattering, but you still can have like this kind of organizational things going on, weird organizational things that are all statistical based. So the difference is this is statistical based and this isn't exactly statistical based. Like this is actually like looking at each atom and how the thing organizes. So if you're going to do a computer simulation, from an experimental point of view, this is much easier. From a computer simulation point of view, this is much easier, right? Because this in the computer simulation, you're actually looking at each thing that's mixing. You're actually saying, I know the position of this, I know the momentum of it, I know everything about that, right? And then I know that about all the other ones too. So the first thing you calculate in computer simulation is the correlation function, right?
There's my mouse up there.
Oh, all right. I wonder where, yeah, I turned it off.
Big bang.
Did you guys do anything weird with the computers in here? Because nothing was working when we came in.
Frankly, I was sitting
No, it's
right
fixed.
here.
It's fixed
Oh, it
now,
is. I
yeah.
accidentally like, bumped a lot of that. I don't know what
Oh,
that is.
all right. That could be it. That explains, you know.
Sorry.
Now we know.
I won't try to mess it up again.
Someone throw something at him. Yeah, it's like, run fast. Yeah. All right. Now we know. It was a party. All right. Things got out of hand. Anyway, yeah, so if you're going down this road, you know, and so when we do simulations, this is the road that you go down, like because this thing is much harder to deal with random organization of things. You know, experimentally, this is easier to deal with, and also in terms of writing a equation of state, like this is so much easier to deal with. And then in terms of simulations, you get this information, you know, and the things do correlate. So basically, it's a better way to do it in a sense. So anyway, this is what you do. You have this Ornstein-Zernike, this is their function, you know, so basically it's like a correlation function. So in other words, this rod throwing thing. So you're going to have, again, like if the rod lands in the thing, then you're going to have like, that's a 1. If the rod doesn't land, so if you start with the rod in one of them and go out and you don't find it, that's a 0. You're going to average over all possible rod throwings a certain rod length. So it's going to be the volume fraction of the things. That would be that the one end lands in the thing. And then maybe the volume fraction squared, because it's going to be the volume fraction of the other thing if this rod is long enough. Like if the rod is really long, then it's going to be the volume fraction squared. Right. So usually you divide it by the volume fraction. Because the one.
Which one again is easier to model?
This one's much easier to do in computer simulations. Because you're putting in like the position and the momentum, and there's a velocity of everything that you put in, like in molecular dynamics, and then you're going to let them move. And when they get close enough, the interaction energy comes into play, and there's a force that makes them go back. Then you're going to move them again. That changes the momentum, right? And the position has changed from the velocity. Then you let them move again. So all you have is like positions and momentum of everything in the system. You have just a table of those. Then you let it move, you let everything go through equation of motion and energy of interaction. then look at it again. So you have time steps like boom, 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 boom. And the whole thing's like weaseling around, shaking, right? And it's gonna, out of that, you'll get like structural form, like something will emerge from it if you're lucky, right? If you get what you want. So anyway, so that's exactly what, and then if you know the position of everything in the world, then you can easily calculate the correlation function. It's just going to be like throw rods into it. It's like yes, no, and it's ones and zeros, which computers like. So you get this number. It's going to be between 0 and 1. And it's going to give you this correlation function. And then experimentally, if you want to measure the correlation function, you Fourier transform it and get the scattering. So the scattering measurement. So this is going to be on a nanoscale, hopefully. Then you're going to do X-ray or neutron scattering to get the correlation, get the scattering and transform that to get the correlation, or vice versa. So you're doing computer simulations and scattering, they're tied together. Like the two techniques are going to be linked. Anyway, so this peak is going to be like the correlation length, like the average length between the particles, which will be like an integral of the correlation function. Right. So that kind of separation distance is the correlation length. Anyway, so the Ornstein-Zernicke is describing the correlation function. So you can have, the simplest case would be like, I'm only going to consider binary interactions, like A and B, and that's it. Like EAB or EBB or EAA, the thing from the Hildebrandt. This thing accounts for, and if you want to describe that system, you need to have all correlations. So you do an integral over, so this is the binary, the AA, BB, AB, and this is the actual correlations of things in the system. And that's going to be the integral of the binaries. So you have the binary correlation, and then you have the actual correlation coupled. Right? They have to be coupled, and you have to integrate over everything, all space, to get that. So because you have a thing and it's defined in terms of itself, then that leads to a problem because you can't get the answer because you don't know the answer. Right? So that's called a recursive relationship. So in order to get the answer, you have to guess the answer. So you need to have a closure relationship to close this thing. So there's like, if you have the closure relationship, then you get the mean field. So it's possible to use this equation to also describe this system, like the Hildebrandt system. And then in that case, it's kind of like rho goes to 0, and then you just get the binary out of it. That's why we just have AB, AA, and BB. So that's called a random phase approximation. And then there's other kind of more and more complicated ways to deal with this that are beyond like what we can do in here, I guess. Like the Perkusiewicz thing is one solution to this thing. So one, like, since you're measuring correlation by scattering, so a natural thing to do is to like transform this to, so you do Fourier transform of the binary of the correlation function and get the scattering, kind of the scattering structure factor. So if you measure the scattered intensity, then you divide by the dilute one. So the scattered intensity has the structure of these things in it, like whatever the thing is there, that has a structure if it's dilute, right? It looks like that in scattering. And when you put it into a mixture, well, it changes, like the original one's the dashed one, and it changes to that, right? So, and then if you have correlations, it has a peak in it. So if you divide the blue by the green, then you get the structure factor, right? So the structure factors is the transform of the correlation function. So you need to get this S of Q. F of Q is what the thing is, and the S of Q is how is it organized. And since we're just looking at how it's organized here, then you can get this S of Q from the measurement. And that would be the same as this Fourier transform as H of R thing. But when you Fourier transform an integral, it becomes a multiplication. So that means you can write a solution to this equation, this integral equation in an algebraic form if you Fourier transform everything. So you can answer what this is in terms of the binary correlations in inverse space, like in scattering space, but not in real space. You can't draw a picture of it, but you can say what the scattering would look like based on the binary interactions. Right. So anyways, that's kind of one part of this thing, is that the inverse space is easier to understand correlations. There's a scattering space is easier to understand correlations in the real space. And then the other, so this is the Perkusiewicz approximation. You write an expression for the binary interactions, and then you can kind of work out an answer for what this correlation function is. It just gets to be pretty involved. So we don't really want to deal with that in here. This is kind of like a separate subject in a sense once you get to that. But it is, you'll see like the Perkusiewicz closure in the computer simulations. Basically, it's kind of like a black box for that. And then you'll also see this Liouville equation to talk about this kind of density fluctuations in time. So all the computer simulations are going to be based on fluctuations. So they use different symbols. So F is the density, and it fluctuates with time. Q is the position, the spatial position, which was R here. So Q is R, and Q here is not R. It's like Q or K here is not the same. All right, Q's position here. So in the computer simulation, sometimes you'll see like Q is the X, Y, Z position of the thing, of each object. So Q is a vector, so it's got X, Y, Z in it, and P is a momentum, like the velocity times the mass. Right, and then there's a time component, and that gives you the density distribution in space. And then if you want to know how it changes with time, you need to know the momentum, the change in density with position, change in density with momentum, and then whatever forces are going into the system. So that kind of balance, that Liouville equation, I think it was invented in the 1800s, but that's like the basis for molecular dynamics, kind of this equation. So you end up with the positions of everything. From that, you can calculate the correlation function. So that's kind of where this thing goes. But we don't really have time to go through this much. Then there's just like the rest of this is just a lot of different modifications to the basically the van der Waals, the Hildebrand approach, right? Talking about, I mean, people parameterize the interaction parameter in terms of like chemical features, like, so you can talk about a acid-base model for the interaction parameter for the Hildebrand model, and you can just calculate what it is from these numbers that are tabulated. And then there's just empirical kind of engineering where you make the expression for the Hildebrand parameter like a two-parameter Margulis model, or you can have any number of parameters that you want, Redlich-Keister model. So you can just have any number of these to make an asymmetric phase diagram, basically. In other words, not symmetric, about 50% composition. And then, so there's just various flavors of this, like various complications that work for different chemical systems and metallurgical systems. There's a lot of them. Like some of them are listed in here. This idea like clustering, like clustering you can count for with this, so you can see there's a different nomenclature for this local clustering thing. Like you have instead of x1, x2 mole fractions, you have mole fraction of 2's around 1 and 1's around 1, and then 1's around 2 and 2's around 2. And then you can write expressions that account for like the interaction between kind of like complicated clustering, like this kind of picture, like where you have clustering going on. And then talk about mixing in that systems. Mostly these end up, even though there's like concepts behind them, like they end up being more or less empirical fits to data. You know, and some work with different systems for one reason or another. So I don't think we need to go through all this stuff. It's too many details, you know. Why don't we quit there and just like leave off these equations, I think, because I'm not sure you're going to retain much of it. And then just go to some computer simulations like Thursday, Tuesday, before Thanksgiving, and the last week we can do experimental stuff, like the last 2 days. Because this stuff, it's pretty dry, and it's like, I'm not sure you're going to retain anything from it. It's just too complicated, you know. So just this homework is enough of a feel for like how you use bookkeeping to keep track of things and how you would apply it to some kind of simple problem, maybe. But it can get a lot more complicated. That's the point, I guess. You can make this so complicated that you know, you lose track of what's going on. So, right, let's quit there.